Welcome back, coders. In this video, we will be discussing the question size, sum, min, max, and find in a BST. So let's discuss the question. So the size function should return the number of nodes. The sum function should return the sum of all the nodes in BST. The max function should return the greatest value. The min function should return the smallest value. And the find function should return a Boolean value. That is, return true if there is node in the tree equal to data, otherwise return false. So this is the demand of the question. You just have to write these 5 functions, try to do it on your own, and then we will discuss the solution of this video. I hope you tried it on your own. So let's discuss the solution of this video. The size and the sum function will be same in the binary search tree as well as in binary tree, because both these functions depend on structure, and those functions who depend on structure of the tree, they are exactly same in binary tree as well as in binary search tree. So let's just directly code these functions. So for the size function, if the node is null, we'll just return 0. Otherwise, we'll get the size of left node, node.left. We get right size, size of node.right. And the total size will be left size plus right size plus 1. And we'll just return total size. The sum function is exactly same. So we're just copying. Instead of size, we'll just return sum. And instead of adding 1 in total sum, we'll just add node.data. So this is sum and size function. Let's talk about other functions. So to find the maximum function, what we used to do in our binary tree, we used to make a call towards our left, we used to make a call towards our right, and we used to ask them to give us their maximum node. So we make a call towards our left, we have faith that it will return its maximum value. So in the case of binary tree, this node will return us 37. We make a call towards our right, and this node will return us 87. Then we compare both these values with node.data and return the maximum value, that is 87. In the case of binary search tree, with the help of the property, we'll reduce the complexity of these functions. So in our binary search tree, we already know that all the values that are present in the left are smaller than the node. So for maximum value, we already know that it won't be present in our left because all the values in the left are smaller than us. So we only make a call towards right. Again, we come to the node, we don't make a call towards left because they are smaller than us. We only make a call towards our right. So we come here, again we make a call towards our right, but the node.right is null. So we just return node.data. So this will be our base condition. If node.right is null, we just return data. Let's try to code this. So if our node.right equals to null, we'll just return node.data. Else, we just return max of node.right. The whole function is same for min also. But instead of making calls toward right, we just make a call towards left. So if node.left is null, we'll just return node.data. Otherwise, make a call towards left because all the smaller data are present in the left. Now let's discuss the find function. To finding a data in a binary tree, how we used to do is, for example, our data is 30. So it will travel all the way to 30, and when it finds the data, it will return. So if we have to find 87, if our data is 87, then it has to travel all the way to the end. It has to go here, here, and then it will find our data and then it will return. But in the case of a binary search tree, if we have to find data equals to 87, we just compare the data with node.data, and if the data is greater than node.data, we don't make calls towards the left because all the values in the left are smaller. So for example, the data is 87, so we compare it with node.data. If data is greater than, so here 87 is greater than 50, so we only make call towards our right. So for 7, we check for 75, our data is greater than 75, then we call towards right only, and we find our data. So if we find our data, we return true, otherwise we return false. For example, let's take an example. If our data is 30. So if our data is 30, we compare 30 with 50. 30 is smaller than 50, so we can make a call towards left. We compare with 25. 30 is greater than 25, so we make a call towards right. Then we compare with 37. So 30 is smaller than 37, so we make a call towards left, and we find our data, so we return true. Let's try to code this. So we have to compare our data with node.data. If our data is less than node.data, we make a call towards left. Node.left along with data. Else, if our data is greater than node.data, we just make a call towards right. We just find node.right and data. Otherwise, if our data is equal to node.data, we just return true. And the base condition here will be if node is equals to null. If we reach null, then we know that we haven't found the data, so we'll just return false. Let's try to run this program. It should run fine. And we are getting a wrong answer. Let's see. Sample input, output. Okay, so our min value is wrong. Node.left is null, return node.data, return min. Okay, we did not change the min. Now it should work fine. Yeah, our answer is accepted. Let's submit this program to check whether it works for all the test cases, and it is the correct answer. So in our find function and max and min function, the complexity becomes log n. So why we use BST is because it optimizes our max and min function as well as find function. So I hope you liked this video. Thank you for watching. See you in the next question.